Hello, this is Neil, and I'll be explaining the delayed choice quantum eraser as I promised a long time ago and never got around to. I'm sorry. So go ahead and click here if you want to watch the delayed choice quantum eraser first, and then you can watch this. Or you can watch this first and then watch that. Matter of fact, that might be better. It might be better to watch this first and then you can watch the delayed choice quantum eraser. I guarantee that after you understand this video, information that presented therein, then you will have a greater appreciation for the delayed choice quantum eraser plus the double slit experiment plus any delayed choice type experiment done. Right, so let's get started. In order to understand the delayed choice quantum eraser better than you might understand it now, is to understand, if you don't already understand these principles, is better to understand the Copenhagen interpretation of quantum mechanics. Now, to understand the Copenhagen interpretation of quantum mechanics is not very difficult. I can sum it up very simply. It is that every particle has a wave function, a probability wave. That's it. What we need to understand more, though, is the Heisenberg's uncertainty principle. Sorry about that, my brain kind of farted on me. Alright, so Heisenberg's uncertainty principle is basically that a particle that has any two related properties, that you can't know both of them with high accuracy simultaneously. The more you know about one, the less you know about the other. Okay, so it works like this. Let's say we want to know that within this area, let's say we have an electron here, and we're going to send this electron in this direction at a given speed, so we know its speed. We projected that electron at a known speed, let's say close to the speed of light. And I have my measuring device somewhere around here, and I'm going to measure the exact position of that electron. To do that, I need to use light. I need to use photons. And so let's say I use a low frequency light. I shoot this low frequency light like this into this region, and because of the distance between the through and crest of the wave, right, there's those big gaps there. I don't know if you can see that in red. Maybe I should draw more up close. There's those big gaps there, and that makes it to where I can't know the position of the electron with great accuracy, right? So I'm only going to be able to know the position with not that much accuracy. Well, interesting enough, this wave here doesn't have a whole lot of energy, but the energy is going to slightly mess up the electron, its momentum. So it's going with this certain amount of momentum. When I bombard it with this light wave here, it slightly changes the momentum of the electron. And because it slightly changes the momentum of the electron, since I somewhat know its position, I have slightly altered its momentum, and so now its momentum is going to lie somewhere within this range, its new momentum. So now I've lost its momentum. So but I didn't learn its accuracy greatly. Hold on, let me demonstrate this better, because I want to show, what if I want to learn the electron's position with greater accuracy? Well, in order to learn the electron's position with greater accuracy, I have to bombard this area with a higher light frequency. And so there's less space in between the wave. Now, I can now know that position, as you can see, with greater accuracy. The problem then is in order to know the position with greater accuracy, I'm having to use higher frequency. What does a higher frequency do? The higher frequency interferes with the electron even more, and now it changes its momentum greatly. So this means the more I know about the position of the particle, by nature of quantum mechanics, the less I will know about its momentum. So now it has a new momentum somewhere within this range, and if I bombard it with a less frequency, less energy, that is less light, I don't mess up its momentum as much. So now I can know its momentum is still within a very small range, so it hasn't really changed that much. So I still know its momentum with pretty great accuracy. But the thing is, I don't know its position with pretty great accuracy, because it can be anywhere along that wave. So the electron could be anywhere within that region. Here, I know it with great accuracy, but by knowing it, once I measure it and say it's here, then I have now messed up its momentum, and now it's within the new momentum that when I have to take another measurement, but I know it's somewhere between there. Okay, here's the thing. What if we were doing this with, let's say, billiard balls or some other thing? Well, if I shoot a billiard ball and I want to measure exactly where it is with light, and the light has a wave, and I want to tell the billiard ball with great accuracy. Well, the photon doesn't mess up the billiard ball. The billiard ball is so massive that the photon just bounces off, and I learn where it's at, but I haven't messed up its momentum. So no, even if I use a very high frequency photon like this, it's not going to mess up the billiard ball because the billiard ball weighs so much. It has so much mass behind it. And so I can know where the billiard ball is with great accuracy without messing up its momentum. And so now I know its position with great accuracy, and I still know its momentum with great accuracy, both simultaneously. This is untrue of the small world due to the small electron actually being the momentum is messed up by the measurement process itself. Not so weird. It's so far it doesn't seem that weird. Okay, so how do we apply this to the understanding then? How does this help us understand the delayed choice quantum eraser better? Well, because the delayed choice quantum eraser is trying even the double slit experiment is actually trying to know or gain information about both position and momentum simultaneously. But before we get into that, let's go ahead and get into the next thing, and that is Josephson junction. Look this up. This is real. It actually exists. The Josephson junction is a technique, a device which regulates the flow of electricity. Wait, that sounds kind of boring. What the hell does that have to do with anything? Well, I'm going to show you what it has to do with anything. Let's say we have this box, and inside this box we have billiard balls, and I'm going to hit with the pool stick this billiard ball here. I can predict with great accuracy that that billiard ball is going to bounce at a certain angle, right? I can make that prediction. That's how pool players can be so good at pool, is they can make accurate predictions on angles and you know where they hit and everything. Pretty basic geometry type stuff. And you can memorize a lot of this angles and stuff in your head, and so you can become really good at pool. Right. Well, the problem is, what if there was some randomness to that? What if billiard balls acted very strangely, and it had some randomness to where it would be, and you didn't know that it would bounce in that direct path or that direct way? That'd be very strange. It'd be very hard to be good at pool. Well, Josephson junction is very cool because the Josephson junction was invented and built around the concept of quantum mechanics. And quantum mechanics says that the electron is neither a particle nor a wave. It is, and this measurement is just partly to understand that, like why it's that way. So the electron will act like a particle when you collapse its wave function and make it act like a particle, but until then it exists as a wave function. That means it exists as a probability wave. This is the probability. This red line represents the probability wave. Now, a probability wave is not the same as an actual wave. An actual wave in a medium, let's say like over here we have this bowl or box or bathtub, and we have water in it, and now we have this wave, right? Because I stuck my hand here and I removed it. Then what happens is I displaced all the molecules of the water, and they begin to shift and they move out of place over here. And there's an empty space where my hand is and the water molecules are not. When I move, that place has to be filled. All those molecules start rushing back into the empty space, which causes this emptiness, which then causes these molecules to go up and then come back around and fill up that space, and these go up and fill that space, and these go up and fill that space, and it causes this constant wave to move across the medium. So a real wave, a physical wave, takes a medium like water, and sound takes a medium like air. That is, it's bouncing off the molecules in the air. But the electron follows a wave that doesn't even exist. It's not real. There's nothing real there. There's no medium. And even the wave itself is unreal. It's a probability wave. It is a function. It's a mathematical function. At least that's how we represent it. But it is a true function. It is a non-existing thing in the universe. I want that to sink in. It's very strange. This is what physicists say. This is real. This has been shown to be real. So the Josephson junction uses this knowledge and proves it's real. It makes a box, right? Or he makes a box and has electrons in here that are going to be emitted inside the box. And since there's a probability wave, which this red line is representing, then the electron can exist anywhere along that wave. Now most of the time the electron is going to exist there. That's the greatest chance. That's the most so we can predict with like an 80% chance that's where most electrons will end up. But it's random. Where the electron ends up on this wave is completely random. We can only predict with probability. That is its position. It's going to be here with an 80% probability. As we get away from that middle point, here and here and here, there's less probability. And when it gets way down here, there's a very little probability it'll end up there. But sometimes it will end up there. Do you see the problem here? The problem here is there's a wall blocking its way. If the electron was a real particle existing in real time at all times, like a billiard ball, and I were to, put a bunch of electrons and shoot them into this box with this, I have my electron emitter here, and this is producing a bunch of electrons. Those electrons would bounce and bounce and bounce, right? That's what they would do. If they acted anything like the real world, or at least the world that we know to be real, that we interact with, like billiard balls, that's what would happen. It would never go through the damn wall. But because the electron does not exist as a real entity until it needs to, it exists as this wave function, then the electron literally exists in probability anywhere along that function. There's an 80% chance it exists here, let's say a 1% chance it exists here. But the chance that it manifests here, and it does happen, although it doesn't happen as much, it does happen, it happens less often than here, it does happen, and so once it exists here, it exists outside the box. As if the electron went through the wall. Here's the thing. The electron never went through the wall. This wall is never disturbed. And so this, whatever you make this out, whatever you make the Josephson junction out of, whatever materials you use, will last as long as those materials last without any disturbance. But if the electrons were actually going, hitting the wall, it would disturb the wall and it would tear down the wall wouldn't last as long, especially if it's a weak material. So that would actually damage the wall over time. But this wall never gets damaged over time by the electrons because due to the understanding of quantum mechanics, which is how this regulator, this device which regulates electricity was made, with that understanding in mind, the electrons never go through the wall. You might have heard that, like in the quantum world, weird things happen, like things bounce right through walls. They don't. They don't actually bounce through the wall. That's misleading. It's not telling it correctly. This is what actually happens. The electron doesn't exist. It exists rather as a probability wave. When the probability wave is collapsed, the electron must exist somewhere along it, and sometimes it exists here, and sometimes it exists here. When it exists here, then it exists here. When it exists here, it exists inside the box. When it exists here, it exists outside the box. That's how it works. It never actually bounced through the wall because it was never on the inside. It was existing as a probability wave, and then it existed here, and now it exists outside the box. So this box inside the box, this generator, is generating electricity, but it's generating it as a probability wave. The electron doesn't exist until it manifests somewhere along that wave. When it exists here, then it exists outside the box, and it never was inside the box. It's important. When it does appear here outside the box, that particular electron never existed inside the box. It only exists as a probability wave inside the box. Does that make sense? Hopefully that makes sense. That's important to understand. And so the few amount of electrons that exist outside the box are the electrons that are used, and thus how this device is an electricity regulator. Okay, and it's very accurate and works very good. Look it up, it's real. Josephson junction is real. It actually works. It proves, it shows that electrons do not exist until they need to exist. Before that, they only exist as a probability function. They're unreal things. That's so weird. They're freaking not real. They're only real when they begin to manifest, and even then, they still only exist as like a wave. Well, I guess they exist as more of a wave function. They begin to they take on particle-like properties, but those are just properties. No different than a video game character having properties. Sure, it has properties. It interacts in its own world based on those properties. Does that make it real? Well, I guess so. It makes it real enough, doesn't it? Okay, so that's that. Unfortunately, I'm going to have to make another video to continue and to show you how all this will better help you understand, if you haven't already started to put the puzzle pieces together, better help you understand the delay choice quantum eraser. Alright, thank you for watching. This is Neil, and I just look like really orange there, or really bright. Oh, that's bad lighting. Okay, let me go ahead and kind of... anyway, bye.